I'm Jamie from Team Delta. Quick question. How many of you have ever been stuck in traffic? We all know how frustrating it can be, right? Over the past few weeks, Team Delta has been exploring the future of our roads, aiming to address some of the challenges that many of us face on a daily basis. Our task was to develop a platooning algorithm. Platooning is a system in which a line of vehicles autonomously follow a single manually controlled leader. Each car collects information about its environment via sensors and messages from the rest of the platoon. This means the distance between vehicles can be decreased, allowing more cars to fit on our roads, reducing congestion. Constant communication and sensor feedback allow faster reactions to dangerous situations, improving road safety. I'll now hand over to Jack, who will give you a brief technical overview of our project.
Thanks, Jamie. So as you all know, when we're dealing with cars, safety is absolutely critical. So we've designed our algorithm to be redundant and decentralized, so that any individual failure doesn't compromise the safety of our passengers or other road users. To achieve this, each vehicle broadcasts its current velocity, acceleration, and turn rate to all the other cars, and they combine this with the proximity sensors and beacon tracking to build up a picture of the rest of the platoon. If a vehicle determines that it's too close to the car in front, it will perform an emergency stop and broadcast a priority message to the rest of the platoon, so it all stops as quickly as possible. To help us demonstrate our algorithm, we've built 3 Lego cars, fondly named DeLorean, Batmobile, and Space Tesla. While integrating with the Lego, we discovered that the processors aren't particularly powerful, so we've had to ensure that we are able to make the algorithm as efficient as possible so that we can run it at a reasonable frequency. We also discovered that the sensors aren't particularly accurate, which meant ensuring safety was quite challenging. To help us test our algorithm more quickly and thoroughly, we built a simulated environment where we control the lead vehicle, and then we can watch how the following vehicles move to make sure that they're doing the right thing. Using the user interface, we can change the algorithm parameters, the sensor accuracy, and network packet loss rate to test it in a wide range of different environments without needing to recompile between each thing. We can also run the simulation without a user interface, which produces a file containing the locations of the vehicles at various time intervals. And then this data can be imported into a data analysis tool to get a more empirical analysis of whether your algorithm is actually working. So I'll now hand over to Aaliyah, who'll talk a bit more about the future of our work.
Thanks, Jack. By designing our code to be modular, with a versatile interface, and then publishing it on GitHub, we hope that other researchers can easily integrate our work with their own projects. For example, they could use the failure injection in our simulated environment to test the fault tolerance of their own designs, or test their own prototype vehicles with our algorithm. Vehicle platoons are already being trialled on roads in the UK and across the world. The results are promising, particularly with large vehicles such as lorries. Platooning may be the next step in the evolution of driver assistance and might eventually become part of a larger, fully autonomous driving system. If you're interested in this topic and would like some more information, please follow the link on the slide to read the research paper which we used as a reference for our project. Special thanks to Jan and William from IMC, and thank you all for listening.